All right, Daniel here, welcome back. So now that you have more experience with higher order functions, let's talk a little bit more in depth about map, flatMap, and filter on actual Scala collections from the standard library, and also introduce 4 comprehensions, which I promised I would do way back in the expressions lecture. Alright, so in the IDE, we'll make a new Scala applications in the part 3 functional programming package as usual. So right click, create Scala class, and let's name this map, flatMap, filter 4. Make this an object, and finally, of course, extends app. Alright, so you've now implemented your own map, flatMap, and filter in your MyList implementations. They are extremely used in Scala and throughout functional programming in general in the standard library. So we'll now introduce the official versions of map, flatMap, and filter along with the official list collection. Alright, so having implemented your own list, these guys shouldn't be too sci-fi. So if I create a new list, and on the right hand side, I'm going to say simply list with 1, 2, 3. And if I print line this, and if I right click and run, now just wait for the code to compile, and we'll get this guy, list with 1, 2, 3. This is the standard library list implementation. And notice that I'm creating a list by calling the apply method on the list companion object. Now, the list standard library implementation also has the kind of methods that we implemented in our MyList implementations. For example, the head and tail methods, plus the functionals that I'm going to introduce here, the map, flatMap, and filter. So of course, head is 1 and tail is list of 2, 3. And if you're curious to see how the map function is implemented, you can simply search list here on scalalang.org and look for the map member, which has the same signature that we used in our MyList implementation. So this was map. Filter is also very straightforward, and it has the same behavior. So if I have list.filter and say I filter and only want to keep the even numbers, and I say underscore mod 2 is equal to 0, then that will print the list with only the element 2 because other elements do not pass the condition. Alright. flatMap also acts in the same way. So flatMap says if I have a function that turns in an element into a list, so let's say toPair is a lambda that turns an x, which is an int, into a list of ints, let's say x and x plus 1, which was the example that we used way back in MyList. So if I print line list.flatMap toPair, then I should be seeing the concatenation of the application of toPair on each element of the list. So toPair of 1 will return the list 1, 2, toPair of 2 will return the list 2, 3, and likewise the list 3, 4. So I should be seeing the concatenation of all. So I should be seeing the list 1, 2, 2, 3, 3, 4. Alright, so this is exactly what is printed out to the console. So this mirrors exactly what we implemented in MyList. So this was why implementing MyList throughout the course was so important. You're probably seeing map, flatMap, and filter as something not extraordinary right now. So I'm going to pause the lecture halfway and give you a small exercise. So try to print out all combinations between two lists. So if I have, let's say, numbers, which is a list, and I have the list 1, 2, 3, 4, for example, and a list called characters, which is a list of, say, A, B, C, and D, I want you to print all possible combinations of them, like you would print all possible chess squares. So I want you to print list of A1, A2, and so on and so forth until D4. So try to pause the video and think about how you would do that. Now, this exercise is a test in thinking style, because in more conventional programming languages, we would simply use 2 loops and be done with it, right? You would solve this without breaking a sweat. But in functional programming, I said that instead of loops, we use functionals and recursive functions. And in this case, we're going to use map and flatMap, which traverses the entire collection. So the solution to this would be something like, let's call this combinations, is numbers dot flatMap, because for each element in numbers, I'm going to generate a list. So for each number in numbers, then I'm going to traverse characters now. So characters dot map, and for every character, I'm going to return the string composed from the character and the number. So string plus the character plus the number. All right, let's print this out. So right click and run. So of course we print all the possible combinations, A1, B1, C1, D1, all the way to D4. So this is how you would transform loops in more conventional languages into functional code. So if you have 2 loops, you would do a map and a flatMap. If you had 3 loops, for example, if I had colors, which is a list of, say, black and white, then if I wanted all the possible combinations of numbers, characters, and colors, then I would do characters.flatMap this time around. And for every character, I would do colors.map. And for every color, I would get empty string plus the character plus the number plus the color. And I think I need to close one more parenthesis. So if I right click and run this, I should be seeing A1 black, A1 white, B1 black, B1 white, and all the possible combinations to the end. Notice that this blows up quite a bit. Let's put in a dash here so that it's a little bit prettier at print. All right, so you get all the possible combinations between a list of numbers, a list of characters, and a list of colors. So this is basically a 3-way loop, which is composed in functional code of 2 flat maps and a final map at the end. So this is how we do quote-unquote iterations. Right? Okay, next thing that I want to talk about is Foreach, which is similar to map, only that it receives a function returning units. So if I do list.foreach print line, then this will print all the numbers 1, 2, 3 on a separate line. This is exactly the same as we implemented in my list. So we now know how to process multiple lists with map, flatMap, and filter, but in practice, all these chains will get increasingly hard to read, especially for other people. So if you write this line, it's understandable for you, but other people will take quite some time to understand what you meant. So in Scala, we have a shorthand for all these chains, and they're called for comprehensions. So watch how I would rewrite combinations as a for comprehension. So I'm going to say val for combinations equals, and I'm going to put in the keyword for, and I'm going to open in curls some curly braces. And inside, I'm going to say n left arrow numbers, c left arrow characters on a separate line, and color left arrow colors. And at the end, I'm going to say yield, this is a keyword, and I'm going to put in this expression. This is exactly equivalent to the map and flatMap chain that we wrote above. This expression is rewritten by the compiler to chains of maps and flatmaps. But I think you will agree that this way of writing it is much more readable. So if I print line for combinations, I would get the same result. Yes. So if I uncollapse this, you'll see that the result here and with the 4 combinations are identical. Now, if I want to filter out some of the, for example, numbers, I would put in what we call a guard. So I would say if n mod 2 is equal to 0, so I'm just filtering to keep only even numbers. And if I print this out, I'm going to get all the combinations between characters and even numbers and all colors. These are translated into a filter call for numbers. So before flat mapping it, the compiler would write something like filter this guy. So this is what happens when you put in an if guard in for comprehension. But right now this chain right over here doesn't even fit into the whole screen. So for comprehensions are much more readable and are preferred in practice. Now, if you want to do side effects like the for each thing, you can still use for comprehension. So if I say for n in numbers, print line n, then this is equivalent to numbers for each print line. I'm saying equivalent, but it's actually identical because the compiler takes care to rewrite this for comprehension into an actual functional call. Before I move on to exercises, I'm going to add one more little syntax overload, which is, again, sometimes used in practice. So if I say, for example, list.map, and I want to multiply each element by 2, an alternative syntax to that would be to say space, and then open a curly brace, and say x arrow, and then provide an implementation here, x times 2. So don't be scared if you see this syntax in practice. All right, now exercises. First exercise, I want you to try to see if my list supports for comprehensions. Given that we said that the compiler rewrites for comprehensions as chains of map, flatMap, and filter and for each. I think you'll be surprised. Second exercise, I want you to implement a small collection of at most one element. I want you to call this maybe, and we'll make this covariant. And the only possible subtypes of this are going to be an empty collection or an element with one element of type T contained. And I want you to implement map, flatMap, and filter for this collection. So pause the video, think through these, try to solve them, and I'll come back with solutions. Now, let's go through the exercises in turn. First exercise says, my list supports for comprehensions, ? Well, for comprehensions are rewritten by the compiler into chains of map, flatMap, and filter. But for that to work, we need map, flatMap, and filter to have a special kind of function signature. So map needs to receive a function from A to B, and this guy should return a mylist of B. Filter should receive a predicate, which is from A to Boolean, and should return a mylist of A. And flatMap should receive a function from A to mylist of B. So just in the same style as list, and this should return a mylist of B. Now let's check our function signatures. So let's see. So map receives a type parameter B, which receives a transformer from A to B, which is a function from A to B. flatMap receives a transformer, which is of type A to mylist of B, and filter receives a predicate, which is A to Boolean. So this is exactly what we need to be able to use for comprehensions. Let's switch back to map, flatMap, and filter and for, and try to see if our mylist implementation actually works. So let's just say we have, actually, you know what? I'm going to switch back to mylist because I want to test for comprehensions here in the mylist file. So if I say for a number, arrow left, list of integers, and say list of strings, let's say a string in list of strings, I say yield, and let's just yield n plus a dash plus the string. Notice that this expression actually works, but that's because our definitions for map, flatMap, and filter have these exact function signatures. So this was an intentional design so that we could get to this point. If you have any other kind of function definitions for map, flatMap, or filter, the for comprehension will not work. So if I say val combinations equals for whatever, and I print this out, combinations, then I should be seeing all the combinations from 1, 2, 3 and hello Scala all chained with a dash, right? So 1 hello, 1 Scala, 2 hello, 2 Scala, 3 hello, 3 Scala. So the combinations work. Now, for comprehensions, of course, are expressions. So I can simply paste them into the print line statement, just to prove that for comprehensions, like everything else in Scala, are expressions, right? That evaluate to a value. I'm just gonna Control Z this one because I've proven my point. So it seems that as a bonus, our mylist implementation has the nice feature that is compatible with for comprehensions. This is pretty darn cool, and this is something to bear in mind if you want to implement your own collections. If you want to make them compatible with for comprehensions, all you need to do is provide map, flatMap, and filter functions that look like these. Alright, so let's switch back to map, flatMap, filter, and for and implement exercise number 2 with the maybe collection. Maybe is often used in functional programming to denote optional values. And we're going to discuss about the actual option type in Scala, but I wanted you to get a sense of how this single element collection looks like. So we would create a little abstract class. Let's actually write this in its own file. So if I go ahead to the exercise package and I create a new Scala class, I'm going to name this maybe. And I'm going to make this an abstract class, just like the list. Switching back to presentation mode. Now this abstract class maybe will take a type parameter, which I'm going to make covariant. And just like the list, will be extended by 2 case subtypes. By case object, let's call this maybe not, which will not contain anything, but it will denote the absence of a value. And this extends maybe nothing. And then we have a case class, let's call this just, with the type t. Again, covariant, and this will contain a value, which is of type t, and extends maybe t. So in just the same fashion as we did with list, we have an empty quote-unquote collection and a full quote-unquote collection, and this guy holds just one value. Now we said that this abstract class maybe wanted to have map, flatMap, and filter. So let's define a map. Map with type parameter, let's call this b, and a function which takes a t and returns a b. And this will return a maybe b, just like we did with list. FlatMap will also take a type parameter b, and it will take a transformer from t to a maybe b, and this will return a maybe b. And filter doesn't receive any type parameters, but receives a predicate from t to boolean, and it will return a maybe t of the same type as the original. So let's go ahead and implement these in the subtypes below. So for maybe not, map is going to be, let's call it def map with a type b, and it receives a function from nothing to b, and in just the same style as list, this will return a maybe b, and it will return maybe not. So basically empty.map something, some function, it will still return an empty quote-unquote list. All right. Now flatMap receives a type parameter b and a transformer from nothing to maybe b. This returns an maybe b. And again, empty.flatMap a function returns empty, so maybe not. Okay, now filter doesn't receive any type parameters, but it receives a predicate from nothing to Boolean, and it returns a maybe nothing, and of course will return maybe not. Again, empty collection dot filter with some predicate, it will still return an empty collection. Now, in the case of just, we'll actually need to provide some proper implementations. So I'm going to copy them over. For map, if I have a collection with only one element, then I will still return a collection with one element, and the value will be the result of applying f to the value that I currently have. So this will return just with the value f applied to value. Okay? flatMap. flatMap is easier than you might think. So in the case of list, we concatenated the application of f to the head and then concatenated that with whatever flatMap did for the tail, but we have no tail here. So we'll just return f of value. And for filter, then we need an if condition. So if p applied to value is true, then I'm going to return this same object. Otherwise, from a collection with one element, I'm going to end up with a collection of no elements, so maybe not. All right, so this is the implementation that we wanted. Let's write a simple application to test our code. So object, let's call this maybe test extends app, which will make our code runnable. All right, now maybe not is not so interesting. Maybe it's not interesting because map, flatMap, and filter will simply return maybe not. So there's nothing really to test. So let's say we have a value called just 3, and we'll just construct a just object with the value 3. And let's print first this guy, and then let's try to play around with it. Let's say just 3.map, and let's multiply the value inside by 2. Then let's write a flatMap. So just 3.flatMap, and from the value inside, we're just going to return a just with underscore mod 2 equals 0. Actually, underscore here is not really known, so I'm going to write in a proper lambda. And let's write just 3.filter with the same lambda. Okay, so just 3 will print just 3. Just 3.map with this lambda which multiplies by 2, this is going to end up with just 6. And this guy, just 3.flatMap, where I'm creating a new just object with a boolean inside, this is going to be a just false. And this guy is going to return maybe not, because just 3.filter, and the predicate is not going to pass for the value 3. So from a just object, I'm going to end up with a maybe not object. So let's see if our assumptions hold. So we have just 3, which is the original object, just 6, which is the mapped with the multiply by 2, just false with the result of the predicate here inside, and maybe not, because I've just filtered a collection with at most one element by a predicate which does not pass for that value. Now, at this point, you might be wondering, Daniel, like, wait a minute, what the hell are you doing? Why on earth would I want to create a collection with at most one element? But I'm here to tell you that this maybe thing that you wrote here is extremely important. And it's not that it's a collection with at most one element, because if you used it as a collection, then yes, it will probably be useless. But the philosophy of the maybe class here is to denote the possible absence of a value. This is extremely important, and we'll deal with it in the options lecture later in the course. For now, take a step back, relax, and I will be waiting for you in the next video.